Hello, my name is Xamiliotti and I'm a PhD student of University of the Aegean in cooperation with Leuphana University of Lüneburg. The title of my presentation today is about microstructure and mechanical properties of laser beam-welded aluminum alloy 2198 using aluminum silicon filler under post-weld heat treatment. I will first motivate, then explain the procedures, present the results, and finally conclude. Beginning with the technological problems, all traditional design of aircraft structures have been made by fastening differential structures with rivets. It is obvious that riveting increases structural weight. The new trend involves joining techniques as to replace riveting with fusion welding. It is estimated that structural weight can be reduced by 15% and respective cost by 30%. Lithium is a metallic element with low density. Therefore, it was introduced to aluminum alloys to reduce weight. Nevertheless, this attempt had specific disadvantages, for example, high anisotropy in the mechanical properties. Aluminum alloy 2198 is a third-generation alloy with lithium and copper addition and has been recently developed. This alloy is a precipitate alloy. By this I mean that with natural aging or with artificially aging, the quasi-static properties are changing. We don't have one mechanism, but we have 4 different, so that makes the situation more difficult. But why we need these precipitates? Because they are blocking the dislocations. By blocking the dislocations, you can increase strength and you can sacrifice ductility. The tensile mechanical behavior of various artificially aging times was examined in the literature. Here we can see stress-strain curves with increasing aging times up till 900 hours. More analytical, yield stress continuously increases with aging time up to 8 hours. This increase in yield stress is characterized as under-aged region. A plateau in the yield stress was noticed from 8 hours up to 48 hours aging time, which is a characteristic for the peak aging condition. Finally, by further increasing the artificial aging time to 98 hours, there is an essential decrease in the yield stress due to the coursing of the precipitates, so this heat treatment condition is considered to belong to the over-aged region. Continue with the experimental procedure. We investigate aluminum alloy 2198 with 5 mm thickness. Some of the seats were autogenously laser beam welded, and some of the seats were laser beam welded with filler material. Then the seats were post-weld heat treated at 170 degrees. From both welds, tensile specimens were machined, and then we had the microstructure analysis, the mechanical testing, the evaluation, and the conclusions. For the weldings, we used fiber laser with maximum 8 kW power. Argon was used as a sealing gas for both autogenous and non-autogenous welds. For non-autogenous welds, aluminum silicon 4047 used as a filler material. Here we can see also the welding parameters they used. This slide depicts the standard tensile specimen geometry according to the ASTM specification. The artificially aging heat treatments were performed in the furnace for 170 degrees and for 3 different artificially aging times, which were selected according to the literature, namely 3 hours, 48 hours, and 98 hours, in order to correspond to underaging, peak aging, and overaging conditions respectively. The mechanical tests were carried out at Helmholtz-Zentrum Hereon with testing machine using maximum tensile load of 100 kN. Continuing with the analysis of the results, here we can see hardness Vickers versus distance from the weld center for autogeneous welds under different artificially aging conditions post to the weld. With increasing aging time, fusion zone presents similar hardness for all conditions. Higher hardness can be noticed for peak aging condition and 48 hours. Non-autogeneous laser beam welds and with increasing artificially aging times present higher hardness compared with autogeneous welds, which can be attributed to the exploitation of the filler wire and the increase of silicon content. For the metallography analysis of autogeneous welds and non-autogeneous welds, transition zone divided in two more zones: the aqueous zone and the partially melted zone. The aqueous zone contains aqueous grains with random crystal orientation. Fusion zone next to aqueous zone is composed from columnar grains and in the center of the fusion zone with aqueous dendrite grains. Non-autogeneous welds shows a narrow aqueous zone due to the low thermal energy during welding when compared to the autogeneous welds. For the tensile stress-strain curves of the base material and with increasing aging time, total elongation at fracture reduce from 24% to 13%, while strength increase up to 48 hours and peak aging condition. For autogeneous welds and with increasing aging time, ultimate tensile strength increase up to 260 MPa, while total elongation at fracture decrease from 4.5% to approximately 1%. Comparing the specimens with and without laser beam welding, there is an obvious decrease in ultimate tensile strength as well as in total elongation at fracture. For non-autogeneous welds, and with increasing aging time post to the weld, present a higher decrease in ductility and an increase of ultimate tensile strength up to 48 hours and peak aging condition. Here we can see yield stress versus artificially aging at 170 degrees. Base material specimens present a continuously increase up to 48 hours and peak aging condition. Autogeneous welds with red present an increase from 3 hours up till 48 hours, which approximately 57% decrease compared to the base material. Non-autogeneous welds with blue present similar behavior to the base material samples with a decrease of 32%. Total elongation at fracture and with increasing artificially aging time for base material present a decrease from 24% to 13%. Autogeneous welds shows a decrease from 4% to 2%, while non-autogeneous specimens present a decrease from 6% to 1%. For example, in the as welded condition is approximately 83% decrease for autogeneous welds and 75% for non-autogeneous when compared to the base material specimens. The fracture surface in the laser beam welded aluminum alloy 2198 bad joints for both autogeneous and non-autogeneous welds is mainly located within the fusion zone with a 45 degrees inclined to the tensile loading axis. This fracture behavior is independent of whether the welding joints were produced autogenously or using filler material. Nevertheless, it can be observed that the overall macroscopic topography view of autogeneous joints shows many cracks which simultaneously propagated in the thickness direction, which were reduced in the terms of amount and length by adding the aluminum alloy 4047 filler wire in the non-autogeneous welded joints. The quality indices concept was exploited to select the optimum quality between the different heat treatment conditions of autogenous and non-autogenous laser beam weld of aluminum alloy 2198. Here we can see the definition of quality index according to the literature, where Rp is the yield stress, W is the strain energy density, and A is constant according to the literature. Here we can see yield stress versus strain energy density, while with blue lines we can see the ISO quality index lines. The autogenous joints show high quality for peak aging condition and 48 hours. For non-autogenous joints, it can be noticed that the quality index is higher for all the investigated conditions compared to the autogenous. The highest quality index is presented in the peak aging condition, approximately at 340 megapascal. However, it is questionable if the design engineer will use such a material with limited ductility capability, let's say less than 1%. To this end, this diagram may be used to select specific condition for aluminum alloy 2198 welded joints, which is expected to lead to an acceptable combination of yield stress and tensile ductility. It is to the design engineer's prerequisites on yield stress and tensile ductility capability to decide on the appropriate artificially aging condition with the highest possible quality for mechanical performance. To conclude, higher hardness observed in the fusion zone for non-autogenous welds compared to the autogenous, which can be attributed to the exploitation of the filler wire. Due to the different laser beam power and thermal energy, a wider equate zone is presented in the case of autogenous welds when compared with the non-autogenous. Autogenous and non-autogenous welds of 2198 alloy show a decrease in yield stress in the as-welded condition, approximately 46 and 38% respectively, when compared to the base material. For the case of the post-welding heat treatment, yield stress attains higher values in the peak aging condition. Photographical analysis showed that all failures of specimens were mainly located in the fusion zone of the cross-section of the weld joint, with an approximately 45 degrees axis inclined to the load axis. The concept of quality index was shown that non-autogenous welded joints always have higher quality index than the respective autogenous joints. The highest quality index was achieved for the as-welded and the peak-aged condition for maximum ductility and strength value respectively. Thank you very much.